Hi, my name is Justin Cameraman. I'm the Chief Product Officer at Instnt. I'm going to talk today about what we call the Tango, operationalizing predictive models and engineering and data science collaboration. So first of all, a little bit of background. What is Instnt? It's the first fully managed customer onboarding platform for businesses with fraud loss insurance up to $100 million annually. So what does that really mean? It's essentially identity verification and fraud detection. So there's other platforms out there that do the same thing, but we are fundamentally different in that we've really targeted ease of integration as a primary design feature. Pretty much anybody who's looking to transact nowadays on the internet, e-commerce, financial institutions, onboarding is a big problem, and we try to take that as a fully managed service off your hands so you can focus on your core business. You essentially use our site to answer some questions. We build a sort of an AI-driven onboarding flow, and then you integrate it with a snippet of code on your website or one of our client SDKs. I'm sure you've all seen this diagram before. It's full credit to Drew Conway. It represents all the skills that come together to form a good data scientist. So we have the software engineering and computer science side, the quantitative math and stats side, and then the business domain expertise. So at Instnt, we're producing essentially a data product. We're using historical data to train models to accurately predict whether someone's likely to commit fraud or not, also to verify their identification. So this is the day zero identification problem where we have no knowledge of the person's history. So we have to do a very rapid, pretty much in real time, couple of seconds, gather information on them from the internet, from biometrics that we capture, device fingerprinting, and behavioral metrics, and make a decision in those couple of seconds. So this is meant to represent how in our team those different elements work together as sort of departments or specialties in the platform. We have our engineering side, our data science team, and then we have domain expertise who know the compliance and fraud detection space. So first of all, a bit of background on the engineering team. I mean, this is pretty traditional in the sense that we're following an agile methodology. We're using Jira to manage sprints and delivering features either as time-boxed features or a fixed length sprint. The engineers are focused on building prototypes and then scaling that up. So there's an initial validation of the concept, and then how can we scale that to many thousands, tens of thousands, millions of transactions as we grow our business. The code has to be maintainable. So there's a development lifecycle checks like code reviews. There are commenting standards. There's a choice of language, which really defines the environment that we're working on, and then the platform. We're in the cloud, AWS specifically, but I think these comments sort of apply to anyone, whether it's on-prem or another cloud platform. Repeatability as well. We need to be able to manage our configurations and code versioning so that we can recreate any version in the past for debugging, for troubleshooting, for hot fixing, and for release. So these are all pretty standard engineering things, but they do follow a certain cadence of sprints and deliveries and planning using agile tools. Also on the QA side of engineering, tests tend to be checking for deterministic correctness, where there's a specific set of preconditions, there's an action, and then we match that to what's the expected outcome, and it's either yes or no, does it work? No, this is a bug. Yes, check, it can go and be released. So this will compare this to the QA, which is quite different on the data science side. We're checking quite differently for correctness. And then our diagram showing how these various forces push and pull against each other in elusive pursuit of the elusive unicorn architecture. So on the data science side, very exploratory by nature. We're asking questions. We're using the data to validate or invalidate them. I think either of these is quite important. The model space is potentially infinitely large, and anything we can do to narrow that down to potential solutions aids the the search for optimal models. Strangely enough, on this very quantitative side of the fence, delivery criteria tends to be a lot more subjective than on the engineering side. We are, to evaluate a model or an algorithm, we're taking a sample set, we're removing it from the training set, and then we're evaluating on that afterwards. So essentially, by nature of estimation, there's a assumed error, and we'll check models against each other. If we have a new model that's been trained using a new method or new data, we want to, before we put that in production, we want to make sure we don't get worse in production. We want to get better. So we'll evaluate models over a complete range of operating conditions and then compare them. And it's not unlikely for models to perform better in some operating region than others, and then vice versa in another region. So we really have to be cognizant of where is this model operating for the customer, and you base our assessment on that. Again, maintainability of models. Can they be recreated? Are we keeping track of hyperparameters, training data, labels, etc.? Are we able with an identifier to recreate this model from scratch? Repeatability, very similar end goal. Again, with models, some model training algorithms are stochastic, so they're using random sampling during training. So rerunning a same training run on the same data may produce a different outcome in terms of the fit or the parameter values. So we use techniques to counter this. We will do multiple training runs starting at different initialization points. So once again, it's a little harder than the deterministic correctness on the engineering side to create repeatable model training runs. Not as sensitive to language or platform choices. Usually the popular algorithms will be available in different platforms. Logistic regression can be done in scikit-learn, as well as it can be done in R or H2O or TensorFlow even. The challenge here becomes in when we have a trained model, we want to transfer that into the engineering stack. So then language constraints, etc., become a factor, but the training not so much. And here, when we're validating correctness, we are sort of leaning on the law of large numbers, where in average, if we perform a large number of runs, the expected result tends towards a known value. So we're just using a lot of sampling, a lot of repetition, and through that repetition, we hope to average out and converge closely enough to an expected value to give the big check mark and say, yep, this is good enough to go out. So to produce these great data products, these two sides have to work together very closely. We try to facilitate rapid development, rapid change, but by preserving the natural workflow of each side of the fence. We try to use some guiding principles at Instnt to help us choose methods and processes for collaborating that don't hinder the process, but provide some rigor for scaling up the organization. So first of all, transparency and visibility. We try to make artifacts from both sides transparent, easily accessible. For instance, if engineering wants to know the particulars of a model that was deployed, what hyperparameters were used, what the expected distribution is, so they can do some operational monitoring, that should all be easily available to them in a accessible place. Similarly, data science, if they want to know aspects of model latency, for instance, for some tuning, they should have easy access to the operational metrics on the data science side. And this extends to access to data, especially in startups where there isn't a mature data access platform. Sometimes data scientists are really forced to roll up their sleeves, write some code, do some database dirty work to get what they need. Most data scientists these days are well trained enough to have these techniques and be able to feed themselves in terms of getting access to their data, but this time is taking away from their specialist activity of whether they may be a domain expert in neural networks, so they're not efficiently used if it's difficult for them to get access to data. So we try to use tools and create a platform where they can easily access data and move forward independently for the most part. Then certain deliverables will require these two teams to really be in sync for a release. So in this case, data science is sort of pulled more into the engineering workflow with Jira or Agile stories, where they are tagged as dependent subtasks or interdependencies between work items. So this only occurs if we're, say, putting a new feature extraction code in, for instance. The data scientist would provide the logic that goes into extracting those features. The engineer will have to implement them, and then they'll both have to circle back with QA to make sure that that's been done accurately and prescribe tests to validate that. So once again, there's language constraints. If we develop a model in Python, but the platform is Java, there's some sort of impedance that has to be overcome to getting them from one side over to the other. There's platform constraints as well, which we try to design around through the language. We try to design around minimizing language and platform constraints in getting artifacts from data science over to engineering and vice versa. Anyway, so there's our guiding principles. Now, how have we put that into action? We've tried to create a common development environment that's flexible enough to accommodate both sides, but really puts them on the same page in terms of module dependencies, tools, etc. So we've used the Jupyter Hub platform, which provides access to Jupyter Hub notebooks on a hosted server, so everyone has their own instance, so they don't interfere with each other in that respect, but they're sharing code through a shared file system. They're all using the same version of the modules because that's managed by an administrator. And we're able to access our cloud platform very easily. Since it's in the cloud, it has easy access to all our Amazon services through the Boto 3 library, very versatile, through our Lambda stack, accessing S3, etc., and our RDS databases directly through SQL. Another thing we try to do is to grab common tools that developers and data scientists come up with and put that into a shared internal tool library. So if you've written a nice routine for decoding or decrypting keys, for instance, that can be shared across the team. Everyone has access to it. It's deployed centrally and is then available to everyone. Another thing is you can kick off a long-running job before you leave the office, close your laptop, and it continues to run up in the cloud, and then you just pick up where you left off. So again, these Jupyter Hub designed primarily for use with Python, but it's has a pluggable kernel option. So we use things like R and Julia in collaboration with Python. And there's a wide variety of other kernels that can be used as well. We use H2O for model training. This is easily accessible through client libraries on the Jupyter Hub server. And then we use for dashboarding for operational diagnostics, debugging, things like that. We use things like Grafana, Shiny, IPy widgets to quickly prototype dashboards. They can be throwaway, or sometimes they prove to be useful enough that they bubble up into the product itself. So like I said, common development environment, Jupyter Hub, pluggable kernels, very easy to use, share. Language constraints, not so much because of the pluggable kernels. We can write Lambda, have data scientists mock up Lambda functions in here, and then almost seamlessly transplant them over into the Lambda stack as long as they have the same call interface and are accessing Lambda services through standard interfaces. Again, we use H2O. It's a great platform. It's sort of a lot of language agnostic bindings for training models. And at the end, it generates Java code. So we can just take that Java code and hand it over to engineering, and then they can apply the rigor of scaling it, error handling, making it sort of more robust for production use. And that's a very clear separation from data science. It's a very clear handover and area of responsibility. Dashboards here, Grafana, lovely to use with just some SQL statements. We can do some more elaborate stuff with Shiny, IPy widgets, etc. But really great for prototyping dashboards. And then out of these dashboards, very often we find things that are would be great product features. and they bubble up into the product itself. And then, like I said, once our models are deployed in Lambda, they fall under all the operational bells and whistles that AWS Lambda provides, the serverless architecture. Here's a snapshot of the X-ray dashboard, which provides some really deep diagnostics into how calls are routed through the system, where we're incurring latency, where there were errors. A really deep insight, very valuable for debugging, both for engineers and data scientists if we're looking for latency improvements, etc. Anyway, thank you very much for listening. Hopefully you can get some benefit out of our methods for dealing with the data science engineering collaboration. I hope you'll be intrigued enough to join our workshop later on, where we work through identity verification, rapid feature development and analysis, which leverages all of these techniques that I've described here and puts them to work. Thank you very much.